Hello, ma'am. Hello, ma'am. Ma'am, good morning, ma'am. Hello. Yes, sir.
Ma'am, good morning, ma'am.
Good morning, yes, sir. Yes, sir. Shall we start
Ma'am,
now?
am I
The
audible?
madam is waiting. Yeah,
Okay,
yeah.
ma'am.
Is it
Let's
audible?
start.
Okay.
Yes, ma'am.
Uh,
Good morning,
One
everybody.
second.
It gives me great pleasure to introduce the resource person of this session, Dr. L. Sujata. Dr. L. Sujata is the head of Center of Excellence in MEMS and Microfluidics and professor in the Department of Electronics and Communication Engineering, Radhalakshmi Engineering College, Chennai. She has 30 years of experience in teaching and in research. She graduated with an AMIE in Electronics and Communication Engineering from Institution of Engineers in 1991. She obtained her ME in Applied Electronics from Bardiyar University in 1996. She has done a PhD and postdoctoral research in the field of MEMS at IIT Madras. She is a recognized supervisor under Anna University and has guided three research scholars for her PhD degree. She has published 2 book chapters, 40 journal papers in referred international journals, and in more than 60 international conferences. She has received a Best Woman Engineer Award from Pondicherry Engineering College in the year 2007 and received Dr. APJ Abdul Kalam Award for Innovative Research by Society of Engineering Education Enrichment in the year 2017. She has established a Center of Excellence in MEMS and Microfluidics at Rajalakshmi Engineering College with sophisticated equipments and clean room facilities for in-house fabrication of micro devices. She fabricated micro devices such as micro tweezers, micro heater, MEMS gyroscope, tri-axis accelerometer, digital microfluidics, etc. She has successfully completed 10 sponsored projects and received funding of rupees 7 crores from.
Yes, sir. Yes, sir.
Yes, ma'am?
Yeah, you can continue, but your voice is not audible. I think you muted your mic just to check it.
Ma'am?
Your voice is not audible, pa.
Shall I read again?
No, no. Yeah, it's. Yeah, you read it. The last.
Ma'am, is it audible now?
Yeah, yeah. Now only it's audible.
Ma'am?
Ma'am,
Yes, sir. Just read the last 2 lines. That's enough.
yeah, yeah. That last 2 lines, just you read it, yes, sir. Yes, sir.
Ma'am, am I
Yeah, you
audible?
audible. Just you read the last 2 lines.
Ma'am?
Yes, sir.
Yes, sir.
Yes, ma'am. Yes, sir.
Just you
It's,
read the last
you
two
have to
lines.
read.
What are the projects, madam, getting? Just you read it.
Okay, ma'am. Okay, ma'am.
You repeat only the last 2 lines only. Okay. No need all
Okay,
the
sir.
things. Okay.
Okay, sir. Okay, sir. Ma'am has established a center of excellence in MEMS and microfluidics at Radhalakshmi Engineering College with sophisticated equipments and clean room facilities for in-house fabrication of micro devices. She has fabricated micro devices such as micro tweezers, micro heater, MEMS gyroscope, tri-axis accelerometer, digital microfluidics, etc. She has successfully completed 10 sponsored projects and received funding of rupees 7 crores from various funding agencies such as DRDO, DST, AERB, etc. She is very passionate on research activities on microfabrication technologies and developing chemical and biosensors. Dr. L. Sujata is joining us to give a lecture on silicon micro tweezers with electrothermal actuation. Please, ma'am, you can take the session.
Thank you, Esther.
Thank you, Esther.
Thank you,
Thank you
ma'am.
for the wonderful introduction.
Thank you,
And
ma'am.
I thank Dr. Kavita and Dr. Joseph Daniel for inviting me for this lecture. I'm very happy in sharing my experience and knowledge in the field of MEMS. So I congratulate the team for receiving the grant to organize this Atal FTP program. So let me share my screen. Just one of you, please confirm whether you are able to see my screen.
Okay, ma'am. Okay, ma'am.
Is it visible? Is it visible?
Yeah. Is it visible, ma'am? But just you switch on that the screen share. Just you make it, ma'am.
I have done. You are not able to see?
Yeah.
Is it in the
It's
full
visible
screen
now.
mode?
Yeah, full screen mode. Just you switch it on.
Ma'am, just go for the presentation mode.
I changed it, but sometimes it is not working. Let me
Okay.
just give me
Okay.
a minute. Is it visible now? Is it visible now?
Yes, ma'am.
Okay. Is my slide moving?
Yes, it's good, ma'am.
Okay, thank you. So I'm happy to give a lecture on this Atal FTP program on MEMS during this week. And the topic of my lecture is silicon micro tweezers using electrothermal actuation. So you can note down my email ID and mobile number if you want to have any discussion later on. You can contact me at any time. My mail ID is sujata.l@rajrashmi.edu.in. So the silicon micro tweezers, the reason why I have chosen this topic is this is one of the very successful device we have fabricated under the NPMAS program. So under the NPMAS program,
Madam,
I think,
sorry for the interruption.
yeah, please.
Madam, please unmute your video, madam.
Yeah, sure.
Okay.
Is it fine?
Yeah. It's fine, ma'am.
Okay.
Yeah, you can.
It's okay.
So the silicon micro tweezers is one of the very successful device we have fabricated with the help of the NPMAS program. So NPMAS program, I think all of you might be knowing the National Program on Micro and Smart Systems. And this is the Government of India initiative under which there are 65 national MEMS design centers have been established. And at Rajarashmi Engineering College is we have the NMDC National Men's Design Center, and of course Annamala University also have this center. And during this NPMOS program, the NPMOS program asked to submit the successful design files along with the simulation results for the fabrication. And we have participated all the 3 years. We have submitted the design files along with the simulation results. And these design files from various institutions, of course, every time 5 or 6 universities only participated. And these design files have been compiled together, and this has been sent to the foundries at abroad. And every time they used to say either the foundry is the soy mums foundry or polymums foundry or pisomums foundry. And based on that, we have to go through the design rule checks, and we have to design our devices following the process flow of that particular foundry. So in that way, this silicon micro tweezers is the first device we fabricated during the first year out of the 3 years of NPMOS program. The first year itself, we have submitted this design file, and this design file was very successful, and we were able to fabricate the device successfully at the foundry, and we have characterized these devices at IISc Bangalore at the Sense Center. So I'm happy in sharing these the working principle of these devices, micro tweezers, and its characteristics. And we also published a paper on this work. So the contents of my talk is I'll give a brief introduction to micro tweezers and what are the applications of micro tweezers, and what are the various actuation mechanisms, and the electrothermal actuator which we used for fabrication of our device, and its basic structure, principle of operation, and the simulation. And then I'll move on to the fabrication details, and of course with a characterization, with the discussion, I'll conclude this talk. So when we say tweezers, all of you know that tweezers are the tool to pick, drag the components. So that is called tweezers, or you can also call it as gripper. So the miniaturization technology based on the microelectronics and MEMS technologies, the miniaturization technology has brought a lot of revolution in the field of sensors and also the actuators. And these miniaturization technologies helped us to develop various micro tools. And one of the micro tools what we are going to see here is the micro tweezers. So the micro tweezers are suitable for precisely manipulating the objects at small scale. So when the components are very small, when it is difficult to handle by your bare hand, then you need the micro tweezers, and these tweezers can manipulate the objects. So the applications of these micro tweezers are in the field of biomedical and biological fields. For example, it is highly useful in tissue engineering labs, and in biomedical during surgeries they use the devices, and micro assembly of microelectronics, where the microelectronics, where you would have seen that SMD components, surface mount devices, which are so small, and handling, picking, and placing in the right position is done by the robotics with the micro tweezers connected with the robotics. And in communication devices also it is used, and wherever you need to do precision machining, these tools are highly useful. And there is a great demand for micro tweezers or micro grippers with a controlled grasping force and accuracy. You should be able to control it very well, and it should show a good reliability as well as repeatability and accuracy. So this type of devices, when usually it comes along with a system, and these things we are always importing. And the fabrication of these devices, then it has to be assembled in a system, then it can be used for a particular application. So these are the areas which are the upcoming, as well as a lot of youngsters have to focus on fabrication of these devices. Developing, enhancing the knowledge in this domain is highly important for the futuristic work. So the features of micro tweezers, what are the features we expect or a micro tweezers. Micro tweezers should be easy to operate. Therefore, you need to integrate with what are the right type of packaging is required, and also it should be easy to operate by even the layman. And a large displacement is preferred for example, if you are applying a voltage, and for the applied voltage, I expect I should get large displacement or large force should be developed. And I also prefer low power consumption for the device, and better if we can operate at low temperature, and mainly the device should be of low cost. So these are all the preferred features for micro tweezers. But whatever the mechanism you follow, we cannot expect all these things can be satisfied. Either the cost may be high, you can see that. So the various driving mechanisms, it can be the tweezers, nothing but it is an actuator, where the actuation can be by electrostatic or piezoelectric, or it can be pressure based, or using shape memory effect. So various transduction principles can be used, and you can develop the actuation force using these techniques. But sometimes you can see that the electrostatic may require high voltage. Similarly, piezoelectric may also require high voltages. Pressure, the device structure may become complicated because it needs the pneumatic pressure to be housed, and shape memory effect, it shows low efficiency, limited operating temperature, and difficulty in position control, all these things. So when you look at electrothermal actuators, from the name, you can understand that it requires electrical voltage and a temperature will be developed. So it involves the electrical effect and thermal effect, and finally it will make the actuation. So here the electrothermal actuators need a high current, and power consumption is also high compared to other type of devices. And also it is usually operated at high temperature. When you pass high current, automatically the temperature will also be high. But they are able to deliver large force, large opening displacement, and highly reliable, and also it is CMOS compatible. So it has its own advantages. When it is CMOS compatible, it is easy to integrate the electronics, as well as it is made up of silicon, so that either integration of electronics or on the same device, same chip, you can have the other parts also. And since it is silicon, it is highly reliable. And the force is also high in electrothermal actuators. So let us see how it works.
Sorry for the interruption, ma'am. Your voice is breaking, ma'am. It's not.
Yes. Is it fine now?
Okay, ma'am. Okay, ma'am.
Yeah.
You can continue, ma'am.
Yeah. So let us see how. Yeah, please. So let us see how the electrothermal actuator works. So this is the basic structure of an electrothermal actuator which we have taken, and generally the actuation, you would have heard about bimorph structures, where two different materials will be connected together, and two different materials, and it will be connected together, and when you apply voltage, the temperature created on the two structures will be of different, and it will make the actuation. It will start bending. So here the whole structure is made up of a single material. It is the ash color, light ash color, whatever you see here, it is made up of silicon. And this silicon, the dark black, is the metal contact. So on this metal contact, you have to apply voltage. And what do you see here? It has a thin, long structure. The width of this beam is very small when compared to the width of this beam. So these thin, long beam and the broad beam, these two are connected in series, right? With the connector. This part I am calling this as connector, and this part we are calling it as fluxer. Now the long, thin arm and broad arm are connected in series, and when you apply voltage, you can see here, when I am applying voltage, DC voltage, for one end I am applying positive voltage, for the other end I am applying the negative voltage. When you apply voltage, the current will pass through the long thin arm and the broad arm. The same current flows through both the beams because they are connected in series. So if you look at this one, the area of this long thin arm, the area will be less. Here the area will be more. So if you look at the current density, here J is equal to I by A. So the area is less, so the current density will be high here. Here the current density will be less. So what will happen whenever you pass the current through a wire, the wire will get heated up. It acts like a resistance, and that based on the material properties and the structural dimensions, you can see that the resistance will induce the heat, that is called Joule's heat. Everyone would have studied about the Joule's heat. So the heat will be developed here as well as here. But when the current density here, it is very high, current density is low here. So what will happen? The materials are same, but the current density here it is high. Here the current density is low because of the area, difference in the area. So what will happen here? The temperature will be very high. Here the temperature will be low. So that this arm is called as hot arm. This arm is called as cold arm. The temperature on this thin long arm will be very high compared to the other broad arm. So that we call this one as hot arm, this one as cold arm. And this structure will try to attain the thermal equilibrium so that it will start bending downwards, that is towards the cold arm side. So you can see the arrow mark, it will start bending towards the cold arm side. So now the actuation takes place. So it started moving. So this principle, we are using it for the tweezers. So how to use this structure or this principle for tweezers? Before seeing that, let us see how this works in a simulation. And for the simulation, we have done the simulation using COMSOL multiphysics. And the material properties are nothing but the properties of silicon. The silicon Young's modulus 170 GPa, Poisson's ratio 0.28, thermal conductivity 130 watts per millikelvin, meter Kelvin, sorry. And coefficient of thermal expansion, electrical resistivity, everything we have taken the standard silicon of what is available on a soy wafer. So based on that, we have chosen these values and we have carried out the simulation. I think this is a video. I have to go to the PPT mode to show the video. Otherwise, just let me show the video. You are able to see this?
Yes, ma'am.
Yes.
Yes, ma'am.
I think the full screen mode, you said it is not working. You can see here the actuation, it starts bending towards the cold down. You want to see again? So this is after simulation, you can go for the animation mode, and when you increase the voltage, it will start bending more and more. Right?
Why is it visible, ma'am?
Okay, right. Thank you. So let me go back to my slide. Okay. So can you see my screen?
Yes, ma'am.
Yeah. So this is the structure. Now, what we have seen is one thin long arm and one broad arm. The bottom structure, which we have seen now, it started bending downwards like this, right? Now I am using two such structures, and these two structures, one is the top structure, the same with the thin arm and the broad arm, that is hot arm and cold arm. Similarly, at the bottom, I have another set of hot arm and cold arm. The thin arm, you can connect it together and take the common contact, which is the ground contact. And the top and bottom, you can give separate positive voltage and for another positive voltage here. So if you want to actuate only the top arm, you can apply voltage to this contact pad and this contact pad, here positive and ground. And if you want to operate only the bottom electrode, then you can use these two contact pads. And if you want to actuate both arms, then you have to apply two voltages, or in parallel, you have to apply voltages to both arms. So the structure consists of a pair of lateral thermal actuators. These are all called lateral thermal actuators because the arm will move laterally, right? The y direction, I can say. This is x and this is y. And through this z direction, definitely it will go into the screen, right? So here you can see it will move in the y direction, the top and bottom. It will move. This one will move towards the cold arm in this direction, and this arm will move towards the bottom direction. What I have done is I have extended this arm. You can see the previous structure. It has only the hot arm and cold arm. What I have done, I have extended this arm, right? So this is what I have done. So you can see this is extended arms. These are the extended arms which I can use it for grasping something or holding something. Okay. So the structure consists of a pair of lateral thermal actuators with hot arms facing each other. The two hot arms should face each other. When current passes, the thin arm gets heated more. I told you already, when the current passes through the structure, the thin arm will get more heat and compared to the cold arm. The differential temperature between the hot and cold arms leads to a net expansion of the hot arm, which will generate the deflection. That's what I told. It will try to reach the thermal equilibrium. To attain the thermal equilibrium, it has to bend. And the deflection is affected by the width of the hinge. The hinge is nothing but the flexor part. You can see that if the length of the flexor varies, you will get different deflection. And here the hinge, they call it is this connecting point. So if the distance between the hot arm and cold arm is more, you will get this connecting the length, connecting point length will be varied. So if you keep as there is when you vary the widths, then what will happen? The deflection will may be different for different lengths of the connecting point and also the flexor length. This is what the connecting point only, it is given as gap between hot and cold arms, and this will be the hinge width is, what is the width here? So the width, if it is more width on the flexor part, what will happen? The movement of this deflection may be reduced. That is, it will increase the stiffness and the deflection will. The smaller gap and narrower beam. You try to keep the narrow beam, very thin beam, as well as the smaller gap between the hot and cold arm we can produce very high deflection. So that I have chosen the structure. You can see the structural dimensions. This I have considered as case 1. I have 2 cases to discuss here. The case 1, I have kept the length of this flexor beam as 100 micrometer, and the distance between the hot arm and cold arm is maintained as 10 micrometer. This I couldn't mention here. So this is 10 micrometer, and the width of the hot arm width, if it is very thin, actually it should be, it is 20 micrometer. The width of the beam is 20 micrometer. The thickness is 10. For the lateral movement, always the width compared to the aspect ratio with respect to its thickness should be high. So that we have taken 20 micrometer as width because the soil wafers comes with the device layer thickness of 10 micrometer. The silicon, the top layer of silicon soil structure, you know, I'll show you the next slide. So the soil structure, the top device layer is silicon. The thickness of that soil layer is 10 micron. So we kept the distance, the width of this hot arms as 20 micron, and this one as 80 micron. And you can see that the structure is extended by the extended arm of 500 micrometer length. So this is the structure we made, and the cold arm width is 300 micron. So now imagine if you want more displacement, I can keep the length of this extended arm as even longer. So what will happen? Whatever the force is being generated, it will start the displacement will be like this. For example, now the arm is this much. Now if I have the length as 1000 micrometer, what will happen? My arm will get ended here, so that I can say I got more displacement. Here the displacement will be this much, here the displacement will be this much if I increase the extended arm. But it is very difficult to increase the length of the extended arm because it will not be a rigid structure. It may get damaged very quickly after operating 1 or 2 times, or when you apply more force, this beam will break. So how can I increase the force without increasing the length of the extended arm? So how can I get the maximum force? So that is the question. And you can see that the device length, total device length is, this is 500, this is 300, and here 100. So totally 900 micron is the device length. And along the width, it is around 500 micron or so, because this is 300. I think the height I didn't mark here, 80 plus 80, this is 20, 20. So around 200 or 300 micron will be in the along the width direction. So the chip size, why I'm talking about the chip length, total length and width is, the NPMOS program, they used to call it as, what is that, real estate. Real estate means they will say that each institution can be given one, for example, 1 centimeter by 1 centimeter area. In 1 centimeter by 1 centimeter, that is 10 mm by 10 mm, you can accommodate how many devices you want. You can draw the diagram and give the structure. So in that way, the real estate is very important. What is the length of my device and the width of my device, and what should be the space I have to give between the adjacent devices for scribing, and also the contact pad should be of minimum 200 micron by 200 micron to take the contact or the soldering of the, that is wire bonding of the contacts, all these things. So I have to accommodate, if my device length is, this is actually around 1 mm. So this is 900 micron is 1000 micron means 1 mm. This is around, for example, that is 1 mm by 0.5 mm if you take, by 10 mm by 10 mm, how many devices we can include. Actually, for the area what they have given is only, I remember it is 11 mm square. 11 mm square means how much? If it is 12, you can write 3 mm by 4 mm. So we were able to, for the given, I don't remember the exact dimensions, but we were able to accommodate only 4 devices. So 4 devices within the space, whatever it was given to us, we were able to accommodate 4 devices. So that's why I have given the names as D1, D2, D3, D4. But for the discussion, I have taken this as case 1. So this device, I have done the simulation using COMSOL. This is the stress analysis. You know the color variations show the amount of stress. So the blue color shows the minimum stress, red shows the maximum stress. Now you can see where is the maximum stress. maximum stress occurs. You can see at the connectors and at the fluxes, right? Because these are the some light green color, which is around here, okay? And in all the other remaining areas, you can see the blue color. So the blue color represents the stress. So the maximum, the lower stress, and the green color represents that is the maximum. Red has not occurred here, but the blue color or the green color is there. So this green color, I have to say, for an applied voltage of 15 volt, the maximum stress at the connectors is connectors only the maximum stress rather than the fluxer. So it is 50 megapascal, which is low compared to the yield stress of silicon. So the silicon's yield stress. So you know the Young's modulus. Young's modulus, from the Young's modulus, you can calculate the yield stress will be 1/3 of the Young's modulus, I think. So it will be 170 GPa divided by 3. Generally, they will take it. So sometimes the yield stress, they mark it as 7 GPa or so, 10 times less than that, like that. So when you compare to those things in gigapascals, here it is in megapascal, which is very, very low. So the structure will be rigid. It will not break easily. For this stress, it will work fine. And the maximum stress occurs at the fluxer and at the connectors. And the stress is low in most of the other parts of the device. So this is what our observation. So this says that the structure is good. You can go ahead for fabrication. That is, you are applying the voltage of 15 volt and you measured what are the stresses in the simulation. Based on the simulation, you can think whether the structure will work fine after manufacturing. So this is the temperature profile. So the temperature profile shows the colors. The red color here, the red color is at the bottom. The temperature of around, these are the temperature in Kelvin. You can see the temperature in Kelvin. The red color shows around, there is 370, 300 Kelvin to, it goes up to 1400 and something, which is almost white color. Where do you see this white color? This is in the hot arm. At the center of the hot arm is the white color. So this white color shows the maximum temperature which occurs at the center of the thin long arm. Not the center here. It is the center of this electrothermal actuator structure. So the center of the long arm, you are getting the maximum temperature. So the center of the hot arm. And thin arms get heated up more than the cold arms. You can see that the cold arms are in yellow color. This is in white color. The temperature of yellow is around 1100. The temperature, maximum temperature is 1470 degree Kelvin. You can see 1471 degree Kelvin here. So this is around 400 or 300 degree Kelvin's difference is there between the hot arm and the cold arm. This is again the video to show how these arms are moving. And this is the simulation we carried out. Let me share again the PPT. This will not work here. So I can go to the PPT mode. Yeah. Hello.
Yes, ma'am.
1 second. Let me share the other screen.
Okay, ma'am.
Showing some. Yeah. Do you see this?
Yes, ma'am.
Ma'am?
Yeah, 1 second. 1 second.
Okay.
Yeah. Can you see the arms are moving apart? Initially, they are straight, and then you can see the upper arm moves upwards and the bottom arm moves downwards.
Ma'am, excuse me, ma'am.
Yeah.
Please share your screen, ma'am. It's not visible.
Is it so? Is it visible now?
No, ma'am. It's not visible. Ma'am, now it is visible. No,
Okay.
no, ma'am. Again, it's not
Yeah.
visible. It's very...
Yeah, I stopped it. I tried to show it
Okay,
in
ma'am.
a different way.
Okay, ma'am.
Is it visible now?
No, ma'am. I think you are not sharing your. Yeah, now it's sharing, ma'am.
Yeah, it will take time actually. So
Ah,
now
yes, ma'am. Yes,
it
ma'am.
is visible, right? So let me play the
Yeah, visible,
video.
ma'am. But ma'am, excuse me, ma'am. Visible, but it's not. We can't
Yeah.
see it in full screen.
Yeah.
Otherwise, you can make it presentation mode, ma'am.
What do you see now?
Yeah, not that PPT slide is showing, ma'am. But you can make it full screen mode.
Yeah, it is not
Presentation mode.
going in the full screen mode actually.
Okay. Okay, ma'am. No
There is
problem.
a problem in the PPT. That's why I moved to PDF. Okay, but to show the
Okay.
video, I have come back to the PPT. So just
Okay. Okay,
see
ma'am.
whether you are seeing this arms moving apart, right?
Okay.
You can see that it is moving, the upper arm moves upwards, and the bottom arm moves downwards. So that is a displacement in the arms.
Ma'am, but
Right? This is the,
animation. Sorry, ma'am.
yeah.
Animation is not visible.
What do you see now?
Ma'am, just to play the video, ma'am.
We are just showing. Just switch on the video.
It is playing actually in my screen. One second.
Right, ma'am. Oh.
Yes, ma'am, now playing, ma'am.
Very good. Thank you.
Yeah, now it's
So,
coming.
yeah, in the full screen mode, it is not working. Okay. So
Okay, ma'am,
this
no
is the
problem. No
simulation
issue.
we
We can
have done.
continue.
Yeah, this is the simulation we have done. And let me go back to the PDF mode so that the screen we can move actually. You're able to see the screen? Hello.
Yes, ma'am, now
Is it
presenting, ma'am.
visible?
Yes,
Yeah.
ma'am, yes,
Yeah,
ma'am.
yeah. Yes, ma'am.
So we observed what are the temperature we get for the applied voltage. So this is the curve we get when you apply, this is the simulation. We applied the voltage from 0 volt to 15 volt and we measured what are the maximum temperature we got and we fixed it with the, that is we compared with the polynomial FET. You can see that it is exactly, yeah.
Ma'am,
Yes,
ma'am,
please.
share the presentation screen, ma'am.
What do you see now?
Your Google Meet screen, ma'am.
Oh. What do you see now? Nothing is visible.
Yeah, it's coming now. Yeah, sharing it.
Okay,
Hmm.
right?
Yes, ma'am. You can continue, ma'am. Now
Yeah.
it is visible. Yeah.
Thank you. So here you can see that when you increase the voltage, the temperature increases. This is the maximum temperature at the center of the hot arm. You can see that the temperature increases, but this is not linear. This is parabolic path. Parabolically it increases with the applied voltage. We have seen that the maximum temperature for 15 volt is 1470 degree Kelvin. That corresponds to 1196 degree centigrade. So why we are looking into this temperature is this, we have to see what is the melting point of silicon. The silicon melting point is 1400 degrees centigrade. Now how much we reached? We reached almost 1200 degrees centigrade. So it is safe to operate less than the 1200. If you exceed beyond 15 volt, it may reach, since it is parabolically increasing, the temperature may reach 1300 or 1400 degrees, beyond which the silicon will melt. Therefore, we should try to operate less than 15 volt, which is the safe operating temperature. So at the same time, you should think about if you are mounting this device on, for example, the packaging, and then where you mount, all these things you have to see, because this temperature, this micro tweezer structure will work fine and you can operate number of times. But adjacent devices, adjacent materials, if you have enclosed in plastic, or if you mount it on your plastic packaging, or if you keep this on your PCB and all, or whatever the materials like soldering paste, or if you are using any other materials, those materials, we have to see this maximum temperature occurs at the center of the hot arm, but the other points, the temperature may be, for example, 700, 800 or so, or it may be 400. You have to think about the other materials, other packaging devices, whatever you use, those things should withstand the temperature which it gets at that point. So you have to take care of all those things. And this is the characteristics of the displacement with, versus voltage. When I apply the voltage, what is the displacement? We have done this simulation for up to 10 volt. What is the displacement? It is around, you can see that the actuation force increases with the temperature. When the temperature is high, you will get more actuation force also. And this temperature is created because of the Joule's effect with the applied voltage. So when you increase the voltage, the temperature will be high and the actuation force will be high. The displacement increases with the increase in voltage. So that the displacement is 24 micrometer for the applied voltage of 10 volt. This is the result I got it on simulation. Now let us see what will happen in the fabrication. Before that, this is the curve which shows the temperature on the long arm. That is the position along the hot arm. The hot arm from 0 to 500 we marked, and the hot arm, how the maximum temperature occurs at the center of the long arm, that is the hot arm. So the this also you can see that the temperature is maximum, and it is like a curved structure where the temperatures are less at the edges of the hot arm. So the temperature profile is, again, this is for the previous one, parabolic fit. And here the device fabrication. The device fabrication, as I told you earlier, this device was designed for the Soy Mums foundry. Soy Mums foundry. Mums is the, here I have written Mums. Mums is a multi-user MEMS processing. So the multi-user MUMP, multi-user MEMS processing foundries. So this soy MEMS is working on the process based on the soy wafer. Soy wafer is the silicon, then buried oxide, again silicon layer. And this silicon layer is 25 micrometer, and generally they fabricate it on 10 micrometer actually. So this is silicon oxide and silicon. This is the structure of the soy wafer. And other than that, what is the overlapping areas, what should be the contact pad area, all those things they have given in the process flow. And the process flow also contains the contact by gold contact pads, so that a metal layer will be deposited on this, and then this buried oxide will be etched, so that the top silicon layer, whatever the structure you created, it will become a freestanding structure. And so the expected features are, when I fabricate the device, we expect that timing response should be very small. It should act very fast. When I apply the voltage, for example, 10 volt, the displacement, it should happen immediately for that applied voltage. So this is the response time. We expect the devices should respond very quickly. And the maximum temperature should not exceed the melting point of silicon. This is what I discussed in the previous slide. And also the stress developed on the structure should be less to improve the lifetime of the device. Stress should be less compared to its yield stress, and temperature should be less than the melting point of the material. And we expect the device should respond very quickly. So with these expectations, we have done a lot of simulations, we observed, and then we made the structure, we prepared the mask layouts. This is the, I can start from here. This is the structure. This is the mask file for the device layer. And this is for the contact pad. You have 3 contact pads. I have shown only 2 devices, but we made for 4 devices. That's why it is marked T2 and T4. And these are the sacrificial oxide, that is the buried oxide layer. These are the mask diagram. So this mask file to be sent to the foundry. And the device is fabricated. You can see this is the scanning electron microscope image, SEM image of the device, whatever we have given the structure. This bright white color is the gold deposited on the contact pad. And these are the silicon. And this dark black shows the bottom silicon where the oxide is removed. So this is the structure, what is fabricated, right? And this structure, we have studied the displacement under the, what do you call, the MSA 500. It's a vibrometer they have, and under the vibrometer, we can see the displacements. So the lower arm moves downward. You can see this is the time. This is the timing response time of the device. Device response time, I have marked it as millisecond. And this is the displacement. We got the displacement. If you take the black color, it moves, the displacement is from -20 to -2.5, that is plus 2.5. And the red color is plus 20 to -2.5. Plus 20 to -2.5. This is the lower arm. This is the upper arm movement. So the upper arm will move upwards, so that it moves from -20 to, you can, don't confuse with the polarities. You can see 20 plus 2.5, 22.5, it is moving, both arms. And one arm moves upwards and the other arm moves downwards. So each arm moves identically, that is 22.5. How much time it takes? It takes only 2.5 millisecond. 2.5 millisecond, it reaches this value. This is for the applied voltage of 10 volt. For 10 volt, the displacement in the simulation, it was around 24 micrometer. Here we got 22.5 micrometer in the fabricated device, and the time taken is only 2 milliseconds. So it responds very quickly. In milliseconds, it reaches 24 micrometer. Each arm moves 22.5 micrometer. And so the displacement, it takes some time to settle down. So the settle down time, I can say, it takes 10 milliseconds. At 10 milliseconds, it becomes flat. Okay. So it takes 10 milliseconds for the applied voltage of 10 volt. to reach the maximum displacement and then to settle down. It takes 10 milliseconds. So this is the very interesting point to see when compared to, you can say that the bulk tweezers, it may take some seconds time, and other devices, it may not respond very quickly, whereas the silicon micro tweezers respond very quickly with the electrothermal actuation. Another important point is we have done another case study. It is case 2, where we changed the dimensions. Here instead of 100 micrometer, I kept it 150, and this cold arm, I made it as 400 micrometer instead of 300. Earlier it was 300 and 100. Now 100 is made as 150, 300 is made as 400, and then of course the device length will be different. I have taken the same diagram to show you, because this diagram I have to dig it out. This we have fabricated long back. So when you look at that, case 1 and case 2, the red color shows case 2. Case 2, what is happening? You get slightly higher displacement because the length of the fluxor is more. When you increase this length, you will get the increase in displacement. So the displacement of in case 2 is 26.25, and in case 1 it is only 24 micrometer. I think this is the simulated results. Again, we have done fabrication also. Experiment values are well matching with the simulation results, and the performance, when you look at these two cases, in case 2 we get larger cold arm length, and also the flexor length is more, and the larger cold arm helps, and the flexor length is high. It helps to increase more force, produces higher displacement at a lower stress. Stress study we have done, stress study on the simulation. The case 2 shows lower stress, and displacement in case 2 is 26.25 compared to case 1, which is 24 micrometer for the applied voltage of 10 volt. And the stress, you can see for applied voltage of 10 volt, stress is 53 megapascal in case 1. In case 2, it is 48 megapascal. So stress is less. So the case 2, it is the highly preferred one, which gives higher displacement with a lower stress. So the lower stress in case 2 will make the device more reliable. And the lateral moving actuators, for the lateral moving actuators, we prefer the high structural thickness, high aspect ratio. That is the actually thickness to the width ratio. And we have taken the thickness to width ratio of 2:1. Actually, I have told you this is thickness is 25 micrometer. This soy mums, they work on 25 micrometer. What we purchase now, the soy wafers are 10 micrometer. Here, this is 25 micrometer, and we made the width as 10 micrometer. So 2:1 ratio will help you to get more lateral displacement rather than the out of plane displacement, that is in z-axis displacement. If you want to avoid the z-axis displacement, you should keep the thickness 2 times compared to the width. That will give you more lateral displacement rather than the out of plane displacement. And the another one which we show here is the current versus voltage. Now we pass the current and we increase the voltage. What is the current? You can see that up to 10 volt or so, you can see that the current is very, very less. Beyond it is near to 13.5 or 14, you can see that the current suddenly increases. In both case 1 and case 2, it increases. Case 1, the voltage is around 13.5. In case 2, you can see that after 14, the current increases. So what is the reason for the sudden steep rise in the current? This, when we dig out what is the reason for this, this is the, because of the temperature, you can say that the intrinsic carrier concentration, which increases. In silicon, you know that the temperature increases. With respect to the temperature, you can see that the electron hole pairs will be generated. So more charge carriers will be injected, and hence you get more current. And if you look at the graph, or you can say that the between 300 degrees, 300K to 1000 K Kelvin, 300 degree Kelvin to 1000 degree Kelvin, the carrier concentration, intrinsic carrier concentration increases from 10 power 10 per centimeter cube to 10 power 18 per centimeter cube. How many times? It is order of 10 power 8. The order of 8. 10 power 8 times the current increases. That's why we are getting the IV characteristics, which is very high. The increase in the current density in the semiconductor increases the electric current, carrier density increases the electric current in the device, and the current shoots up at two different voltages, 13.5 for case 1, 15 volt for case 2. So this is the reason we are getting the sudden increase in the current. And these are the two photographs while we were testing the device. So this is same device, that is case 1 device. You can see this is tested at 2 volt, this is tested at 10 volt. So 2 volt, we get some temperature which is shown at the bright line of the hot arm. You are able to see, right? And at 10 volt, you can see what is happening. It is like a spark. It is a very bright spark. At much, the temperature, imagine it is 1400 degrees or so. So the temperature is very high, 800, 900, 1000 degrees. You can see that the flash, the light flash. And but anyhow, you may think that when the flash comes like this, you will think that the silicon would have been melted, and you think that it may not work afterwards. It would have been that is the structure is no more. It is available. We were thinking, but afterwards we spent just after a few seconds, we found that after it is getting cooled, we can see the structure back. It is there. And we tested each device for more than 200 times, 150 times, 200 times. We tested again with low voltage, high voltage, low voltage, high voltage, high voltage, low voltage. We have done several times and we measured the values. It is very surprising. The silicon, it will not show any mechanical hysteresis. That means, for example, I apply 2 volt. You measure the displacement. For example, the displacement is, assume it is 20 micron it is giving. And I am increasing to 10 volt. The displacement is around 80 micron. Now again I am reducing the voltage. You can see that again it will come back to its original position. That is, for 2 volt, earlier I got 20 micron. Now also it will show 20 micron. And again you stop applying the voltage, it will come back to its original position. The original position is, it is these arms, when it is like this, it is called normally open arms. Normally open arms means normally there is a gap between the two arms. It is normally open. And the displacement between these two arms is 20 micron. And exactly it comes back to its original position. And again, if you measure after it is completely cooled down, if you measure the displacement or the distance between arms, it is exactly 20 micrometer. Every time it comes back to its original position. And whatever the voltage you measure going front and back, again it will come back to its 2 volt. If you measure, again go for 10 volt, again come back to 2 volt, it will show the exact value whatever you got earlier. So in that way, silicon is highly reliable and it will show repeatable values. So it is highly suitable. When you work on silicon, then you will not think about going for other materials. It is suitable because its melting temperature is very high, so that it can be used for any high temperature applications. And this is with respect to resistance, how the resistance, since we have seen the current increases sharply, you can see that the sudden fall in the resistance. This is the inverse of the current versus voltage. Look at what is the power for the displacement. I obtained 24 micrometer or 22.5 and 25 micrometer for 10 volt, right? At that time, what is the power dissipation? We know the current and voltage. So what is the power? The powers are in milliwatts. 100 milliwatt or 1 maximum displacement of around 24 micrometer for the applied voltage of 10 volt. So these are the interesting things. We can see the devices which consume less power which can bring the displacement and which are highly repeatable. And this is the fabricated device. Earlier I have shown videos of the simulation, animated pictures of the simulation. Now this is the video of the fabricated device. Let me move on to the PPT mode to show the video.
Yes, ma'am. It is visible.
You can see this is the video taken while we were testing. So sometimes that is the arm also you can see whether it is moving, and the temperature accordingly you can see. This is, we applied the impulse voltages. So it is not the continuous voltage. We apply the pulse voltages and of the amplitude of 2 volt, 1 volt, 2 volt, and sometimes 10 volt. See, 2, 3, 4, or sometimes 10 volt we apply. That time you can see large movement. And we operated only the upper arm, not the lower arm. We have taken only 2 contacts. We didn't use this contact. So only one arm we tested. Video is over. Let me play again. See. Okay, can I move on to the next slide?
Yes, ma'am.
One second. Okay. Fine.
Now it is okay, ma'am. Sharing. Okay.
When I look at the features of the fabricated device, voltage above 10 volt is not recommended because of the high temperature produced at the center of the hot tub, which may damage the device if you operate at that voltage for a long time. Even earlier it was 15 volt. I told the temperature was 1470, but beyond 10 volt also, we found that it may damage the device if you keep that high voltage for a long time. And also at more than 10 volt, the higher force and displacement, higher displacement produced on any one arm, it produces an impact on the other arm. You can see there is a small jerk in the other arm. When the upper arm moves upwards, it produces a jerk in the other arm because it's a freestanding structure. It produces a impact on the other arm. So the devices of case 1 and 2 has been tested for more than 150 times at lower, higher, and again at lower voltages repeatedly. And we found that the devices are highly reliable. Resistance values vary from 380 ohm at 0.1 volt to 629 ohms at 10.2 volt, which is again a parabolic curve, and then sharply reduces. We have shown that it reduces to 150. From 629, it falls down to 150 ohm at 15 volt due to the increase in intrinsic carrier concentration at the high temperatures. The electrical contacts are provided by chrome or gold contact pads. So the resistance measured while testing, which includes these contacts and probe resistances. So in our experiments, the minimum resistance measured is 100 ohm and the maximum resistance is 1 kilo ohm. So with this, the analysis was good, and the device works fantastically. And as a conclusion, I want to say that micro tweezers have been designed successfully at the National MEMS Design Center, Rajesh Engineering College, and we fabricated using SIMEMS Foundry at MEMSCAP Incorporation. The company name is MEMSCAP Incorporation, and by the files have been compiled and sent by IAC under the NPMAS program. So the fabrication cost was borne by the NPMAS program. And the characterization has been carried out at the Center for Nanoscience and Engineering, SENS Lab at IAC Bangalore. So this gives a lot of, we got a very good opportunity to fabricate a micro device and to test it and to understand a lot about the material properties and also the foundries, how it works, what are the various process flow, how to stick on to it. Now, if you are good at the fabrication process flow and the material science, then you can make your own structure, and these foundries are always available to take up the jobs, and you can send the file, they will fabricate and give it to you. So in that way, any device can be fabricated with the help of the multi-user MEMS processing. So these are available for soy MEMS, poly MEMS, piezo MEMS, metal MEMS foundries are available. And apart from this, now recently this that is NMDC by IEEE Society, they have given a talk on using the foundries at I think where is it is Ireland or somewhere, that Ascent Plus, European country, Ascent Plus, the foundry, they are ready to fabricate the devices at free of cost. It is on nanoelectronics. So anyone is interested, please make use of the opportunity and fabricate the device and test it. So we acknowledge the NPMAS program for the establishment of National MEMS Design Center at Rajesh Engineering College, and also for the support given, financial support for the fabrication of the devices. And then for this is the chip fabrication program. So community chip fabrication program, we thank Professor Anantha Suresh and Professor KJ Vinoy for the immense support for the community chip fabrication program. We also thank Professor Nandita Gupta of IIT Madras for the technical discussions. So thank you. So with this, I stop my presentation. If you have any doubts, you can ask me.
Thank you so much, ma'am.
Welcome.
Thank you, madam, for your wonderful lecture on silicon microtweezers. We hope your lecture on microtweezers will be very informative to the listeners. The device simulation using the IntelliSuite and COMSOL was very well explained. The characteristics of fabricated device for various parameters were elaborated in detail. Now it's the time for participants to raise their questions and to clarify their queries. Participants, you can raise your questions now.
Participants, you can raise your question with ma'am.
There are no questions. There are two options. One is well understood. Another one is not able to follow anything.
Well understood, ma'am. I think so, because you explained a lot.
Hello, ma'am.
What are, yeah, please.
Deep.
Uh, Is your structure is based on the bimetallic strip that we are generally using for temperature measurement?
No, that's what I told. This is not bimetallic or bimorph structure. This is the structure made by a single material, which is silicon. Silicon. Silicon is the only material used in this for the structure.
Okay. So in bimetallic strip, we generally use two different type of metals.
Two different type of metals and the structure will be identical. But here we use one thin long arm and one cold arm. By the way the structure is made, you can get the actuation. Thermal
Ma'am, what
actuation.
would be the application of this
Yeah, that is if you
design?
package it well and after packaging it can be used in the tissue engineering lab or it can be used in the surgical equipments. So we didn't take it ahead for the packaging because we interacted with few companies at Singapore. How can we go ahead for packaging? So first thing for packaging, we should discuss a lot with the company because they are all packaging in the mainly semiconductor devices. Some MEMS devices packaging company are there, but we have to interact a lot, and then we have to give many devices for trials. We have received only 3 chips. Okay, each college they got 3 chips. 3 chips as our device and other people devices are there, and our own devices we made only 4. All 4 are different. And the problem is we have to discuss a lot before going for fabrication, it seems. So in that way, after fabrication, going for packaging, the packaging companies are not interested in doing this 1 or 2 devices to package. So we have to interact from the beginning before going for packaging. Fabrication. We have to discuss about packaging also. Then only we should go for fabrication. If we want to bring it as a complete product. Otherwise, for our purpose, we within the time schedule, whatever the NPMOS has given the time, within the time, we were able to submit the design file along with the simulation results. And then after fabrication, we have carried out the test at the wafer level. We didn't dice the devices.
Okay, ma'am. That silicon that you have used is the properties you have shown initially. Um, that entire structure is based on that property values only. So,
Yes.
like your Poisson's ratio or the gauge factor and so on.
Yeah, correct. The same silicon properties we have given in the simulation and then we fabricated.
Okay,
And
so
we
for other amounts of that properties, it can show some different output. Is it
that,
so?
that is
If we change that Poisson's ratio or the gauge
for
factor or the strength.
no. Generally, the Poisson's ratio may not be a big difference for silicon, and Young's modulus depends on the orientation what you choose.
Exactly.
But mainly, the current which flows through the structure will be different depending on the doping concentration. If it is P type or N type, and whether it is heavily doped or lightly doped or moderately doped, you may get a different IV characteristics, and you may get a different displacement, slightly different. You may get, but whatever the soy structure with the soy wafer, what they use, we got the characteristics like this. So it may be different if you have the doping concentration different.
Okay, ma'am. Thank you so much.
Yeah.
Mr. Deepak Kumar, you can ask your questions now. Mr. Deepak Kumar, are you online?
I think there are some questions on the chat box.
Yeah, yes, ma'am. What is the range of the temperature range?
The
And,
temperature
what
range,
is the-
yeah,
Yes,
but the temperature on the fabricated devices, we didn't measure the temperature because that requires another setup with IR camera. So that one we didn't do. But in the simulation, it shows the temperature of 1470 degree Kelvin. Okay.
Okay, ma'am. And what
From
about the
room temperature
vibration
to
frequency effect in electrostatic actuation mechanism?
we didn't do electrostatic actuation, but we would have done with a frequency, but we have done all the testing with the DC voltage. So we didn't carry out as a frequency measurement or the resonant frequency, those things we didn't measure.
Oh, okay, ma'am. Thank you.
Yeah, welcome.
Participants, any questions? Okay, I think
Yeah.
what ma'am said, all participants they are they understood
Okay.
clearly and very well, ma'am. So really
Okay.
wonderful speak. Thank you, ma'am. Thank you so much for accepting our invitation, ma'am.
Yeah. Thank you, Kavita, because I was
Thank
thinking
you.
what can be discussed. Then I thought whatever we have successfully fabricated, then those things can be
Yes, ma'am.
discussed so that the young faculty as well as students will get motivated and they can also make use of the opportunities available. They can come out with their own
Yes, ma'am.
ideas and new devices, structures, and they can fabricate and they can test it and see. It is one of the achievement, making a micro device and testing it as a working device
Yes, ma'am.
at the micro scale dimension is really an achievement for people like us. So it is really
Yes, ma'am.
interesting when you look at the miniaturized device which you are not able to see on your naked eye, and you have to see the device under microscope, and you have the control on the on its operation. So you can control it, how much it has to move when I increase the voltage, it is actuating. That is very really interesting to see. You have the control over it. So it's really interesting. I
Yes,
expect people should experience that.
yes, ma'am. If you go for fabrication, then we should face a lot of problems. That and all already.
Definitely. But the foundries, when they are available, when your design is correct, when
Yes,
your
ma'am.
principle of operation, what you expect is right, and
Yes,
you have done the simulation and you understood thoroughly, then definitely the foundries they fabricate paka. There is no fault in their fabrication, and
yes, ma'am.
you won't find any much difference between the simulation and fabrication. But
Yes,
when
ma'am.
you try it on your own with the fab facilities, which are that is, you should tune lot. For example, I want to get the thickness, the photoresist also to do the lithography, everything you need a lot of practice, and you should repeatedly do it many times, and you should have all the clean room facilities and the temperature, humidity control, everything. Then only you will be able to come out with the successful devices. But when you depend on when you fabricated the foundries, definitely the devices will come out very well.
Yes, ma'am. Ma'am, one more doubt actually I have.
Yeah.
If you have you fixed any specification for this device, this micro tweezers?
What do you mean by specification is we have to look at the operating temperature
Okay,
and
ma'am.
the stress. These are the factors we have looked into.
Okay,
Other than
okay.
that, the space, whatever they have given, I told you,
Yeah.
no, the real estate, with that you have
Yes,
to
ma'am.
stick on.
Okay, okay, ma'am. Okay, ma'am. Thank you so much, ma'am.
Yeah,
Thank you
yeah,
so much.
welcome.
Okay,
Okay,
ma'am.
it's a wonderful opportunity for me also. I enjoyed the discussion. Thank you
Okay.
very much.
Thank you, ma'am. Thank you, ma'am. Thank you so much.
Okay, bye.
Okay, ma'am. Ma'am,
Ma'am, any feedback link provided, ma'am, in this session?
hello. Hello.
Ma'am, any feedback link provided in this session?
Yeah, yeah, yeah. We will send the session. We will send your mail ID ma'am, shortly.
Okay, ma'am, thank you. Shall we
For
leave?
all the three sessions, for all the three sessions, you should give your post your feedback. And the attendance we have taken only for morning and afternoon session, right?
Okay, ma'am, shall we leave?
Then yeah, you can leave, but all are requested to join at least 11:25 because the speaker will join 11:25. You can join 11:23 like that. Now you can leave.